Hey guys, welcome back to chapter 7. So today we're going to talk about the second application of our stoichiometry. So in the previous video, we talked about limiting reagent, so doing two stoichiometry problems to determine what's the maximum amount we can make of our product. Today we're going to talk about something called percent yield. So another accounting technique for chemists to help us to predict how well we're doing with our chemical reactions. Okay. So first, before we dive into the math, we're going to talk about the concept of percent yield. So percent yield, here is your formula for percent yield. Percent yield is going to be actual yield over theoretical yield. Then we're going to multiply by 100, to make it a percentage. So actual over theoretical. Well, what's actual yield and what's theoretical yield? Theoretical yield is what we could make in theory. So the maximum amount of the product that we could make if we lived in a perfect world. Theoretical yield is going to be what we calculate using stoichiometry. So we're going to use math. Math is a theory. We're going to use math to theoretically see how much we could actually get. Actual yield is the actual amount of product that can be made when the reaction is performed. So if you guys were in a laboratory this semester, you would know, or you would have seen by now, that reactions are not perfect. So we tend to lose a lot of our product to all kinds of things. We could lose it to a side reaction. We could lose it because we're sloppy and we spilled some. Some can be left on the beaker as residue. So there's lots of reasons why we may not get everything out that we put in. So actual yield is when I go into the laboratory, I perform the experiment, and I see what actually came out the other side. For you, actual yield will either be given in the problem, or if you're working on your lab, it's going to be something that you determine when you do your lab. But for us virtually, most of the time, actual yield is just going to be given. So percent yield is going to be the ratio between that theoretical yield and the actual yield. So how much did I actually get out? How much should I gotten out? And then multiply it by 100 to make it a percentage. In other words, percent yield really is the efficiency of our reaction. So if I should get 100 grams out, and I only get 80 grams out, well, then I'm 80% effective or efficient. So it's just, again, another accounting tool to see how efficient my chemical process was. And then if I were to tweak it, did I make it better or did I make it worse? So just another accounting tool. Okay. So here is an example. So if 18.2 grams of ammonia is produced by mixing 6 grams of hydrogen in the presence of excess nitrogen, what's the percent yield? Okay. So let's break this down. 18.2 grams of ammonia. Ammonia, NH3, is our product. So that must be the actual yield. Okay, so when they went into a lab and they actually did this process, they got 18.2 grams from that process. That was their product. How did they get that? Well, they started with a reactant. So they started with 6 grams of hydrogen and tons of nitrogen. So that's, again, just a way of saying, hey, you can ignore that. So what we're going to do is we're going to use that 6 grams and we're going to use it to calculate theoretical yield. Okay, we're going to do a stoichiometry problem to see, well, how much ammonia should we've gotten out if everything went perfectly? Okay, so let's do that. Just kidding. Let's do that on this slide. Okay. So just as a reminder, remember our map goes like this. Grams of hydrogen to moles of hydrogen to moles of NH3 to grams of NH3. Okay. All right, so I'm going to try to tuck it down here in the bottom. And one of the things that I'm going to do in this one, really just because I don't have room, is I'm going to show you a different way to use train tracks. So again, if this blows your mind, don't use it. Go back to the other way. But what I've done up until now is I've broken up these problems into teeny tiny steps. What I'm going to do on this slide is I'm just going to string it together like one long problem. And so I'm just going to use that dimensional analysis and just keep going until I get to the end. Okay. So just like every dimensional analysis problem, I always start with the information that's given. So I'm going to start with this 6.00 grams of hydrogen. Okay. So first step is a grams to moles conversion. So grams on the bottom, moles on the top. And in 1 mole of hydrogen, there are 2.016 grams. Okay. At this step is where I would usually stop it. But now we're just going to continue on. So let's keep track of our units. So grams on top, grams on bottom, those canceled. So now we're in moles. Let's continue. So the next step is going from moles of hydrogen to moles of NH3. So again, I've got moles on top. I'm going to put moles of hydrogen down here. What's my destination? Moles of NH3. Okay. Where do I get the numbers? Yep, the balanced chemical equation. So what coefficient is attached to hydrogen? The number 3. What coefficient is attached to NH3? The number 2. Okay. Let's follow our units again. Moles of hydrogen on top, moles of hydrogen on bottom. We are currently in moles of NH3. Okay. Continue our train track. Moles of NH3 on top, moles of NH3 on bottom. And our final destination is grams of NH3. Okay. So again, just doing grams to moles, moles to grams conversion. I don't know nitrogen. 14.007 plus. So this is 17.031. All right. Follow our units. Moles of NH3 on top, moles of NH3 on bottom, and we're left with grams. Okay. To solve these really long train tracks, you can take whatever path you feel like taking through this problem. You could bounce back and forth. So you could do divide, multiply, divide, multiply. You can multiply all the way across the top and then divide all the way across the bottom. It doesn't matter what path you take. That's the cool thing about multiplication division. Just make sure you get all the numbers in. So I'm going to go ahead and I'm going to kind of bounce back and forth, I think, just because the calculator I'm using right now isn't one of the fancy ones. So I'm just going to kind of bounce back and forth so I can type it in that way. So I'm going to take 6.00 divided by 2.016. I'm going to multiply times 2, divide by 3, and then lastly, I'm going to multiply by 17.031 and hit equals. So I get 33.79 grams of NH3. Okay. So I went through that pretty quickly. I used the new process, but hopefully that was okay for you since you've been practicing these, okay? So what the heck did I just calculate? That's a great question. So let me get rid of all this. All right, so I started with 6 grams of hydrogen and I calculated the theoretical yield. So in theory, if I did this reaction in a perfect world, not one single molecule was lost, I should be able to get 33.79 grams out of this reaction. But when I did the reaction, I only got 18.2 grams. So let's see how efficient we were. So percent yield is actual yield. I'm going to put that in red just so you see it. So this is our actual, is 18.20 grams divided by our theoretical. I'm going to put that in black. So theoretical is what we calculated using stoichiometry. And then that's going to be a decimal number. So I'm going to multiply it by 100 just to make it a percentage. Okay. So 18.20 divided by 33.79 times 100. So this was 53.8%. Okay. All right. So what does that mean? So if I were the chemist in charge of this process and we were making NH3 as a product for customers, so we were making NH3 and that's what we were selling, I would probably be fired because we are wasting almost 50% of what we're putting in, right? So if I put in 6 grams of hydrogen, almost 50%, so what, 40, let me do the math here. So 53.8 minus 100, 46.2% of what I put in goes somewhere else. So whether it gets spilled, it's a side reaction, it gets stuck to the beaker, 46.2% is getting wasted. What that means for a company is that every $100 that I'm putting in, $46.2 is getting wasted, $53.8 is coming out the other end. My boss would probably not be happy about that. So as a chemist, it would be my job to make this process more efficient. You're not going to get 100% yield, but they would probably like to see that up in the 80-85 range rather than in the 50s. Okay, so that's what percent yield is. Actual yield will be given. Theoretical, you will have to calculate using stoichiometry, and then you get a percent out the other side. I hope you guys found this. Oh, no, one more slide. I forgot. So this is just a summary slide that I put together just to kind of read through limiting reagents, read through theoretical or percent yield. And so it's just a nice summary page for you guys to have. So I hope you guys found this helpful.